All right, now let's talk about how probability plays a role in psychology. And we will see how people form probabilities or expectations in reality. Psychologists have categorized many different biases that people have in their beliefs and judgments. And probably one of the most famous ones comes from work of Kahneman and Tversky. They actually wrote a book on their research. It's called Slow and Fast Thinking. It's a popularization of this notion and of the findings of their research. And one of the most important findings from their collaborative work is that people are risk averse or loss averse. So utilities are defined over gains and losses rather than final or terminal wealth. And this is idea first was proposed by Markowitz. He was economist, also famous for Markowitz portfolio, which is currently used. It's an optimization model to find optimal weights for portfolio positions. And this finding is a violation of expected utility postulates. So let's look at an example. Let's say we denote by x and y a bet with gain x and probability y. And let's consider two games. Game A, you win $1,000 with probability 50%. And game B, you win $500 with probability 1, so it's a certain bet. And when those two choices were presented to subjects, to people, then the B was the more popular choice. Okay, so now in this case, you remember, people prefer sure bet. But to begin with, they were given $1,000. So at the beginning of experiment, you get $1,000, and then you were presented with this bet. So you make the following judgment. Okay, I have $1,000 already in my pocket, and then in gamble A, I actually have chance of gaining nothing at the end and basically going back home with zero. On the other hand, if I choose game B, you're actually gonna go home with $1,500. So people say, okay, I would rather, for sure, we'll go back home with $1,500 rather than taking a chance of going home with nothing. Okay, although if you calculate the expectation is the same. It's $500 for both of the gambles. Let's look at another example. Now at the beginning of the game, you are given $2,000 and you're presented with two following games. Game C, where you lose $1,000 with probability 50%, and game D, where you for sure lose $500. Now in this case, actually C was the more popular one. So in this case, you prefer for uncertain game. Okay, so what's the scenario here? You come with $2,000, and then you think, okay, if you choose gamble D, then you're gonna go home with $1,500. And if you choose gamble C, then there is a chance you're gonna go home with only $1,000, but there is also a chance you're gonna go home with $2,000. So people think, okay, I already have $1,000 guaranteed, and I'll take a risk, and I will take this uncertain bet, and maybe I can win more. So people actually behave differently. Although expectations, again, the same here. Expectation for the game D and for the game C is $500. The same is for game A and B. And it seems like if they prefer certain bet in the first scenario, when they choose between A and B games, they should be preferring a certain bet when they choose between C and D. But that's not the case. The key here is that their final wealth positions are identical, yet people choose differently, because apparently they're focusing more on gains and losses rather than their final wealth. So again, that's this finding of Markowitz. And Kahneman and Tversky also studied this phenomenon in their work. So when people are not given any information about prior winnings, they choose B over A and C over D. Clearly, for a risk-averse person, this is a rational choice. And this effect is known as loss aversion. Another bias that psychologists study is what is called representativeness. Representativeness is a phenomena where people take a small sample and calculating frequencies from the small sample and make an assumption that the small sample is representative. They try to extrapolate the frequencies from the small sample to the frequencies in the larger population. So when people try to determine the probability that event was generated by model B, they often use this representative heuristic. This means that they evaluate the probability by the degree to which A reflects the essential characteristics of B. A common bias is the base rate neglect or ignoring the prior evidence. For example, if you toss a coin, a fair coin, 10 times, and out of the 10 times you observe 7 heads, which is quite likely to happen, then what people do, they jump into conclusion that 7 heads is a representative of the true process and conclude that the probability of observing head is 70%. So again, the problem here is that they assume that this sample here is a representative sample that actually represents the true process. And in COVID days, I unfortunately heard several times people saying that, oh, I don't know about COVID. None of the people I know have COVID. And so this is pretty much example of this representativeness bias that people use. They assume if nobody in their circle have COVID, then means that in the larger population of the country or of the world, also COVID is not something that we should be worrying about. Okay, now let's talk about the postulates of expected utility theory. This is rather straightforward. So let's say you have P and Q be the two probability distribution of risky gambles or lotteries. And we might consider the compound or mixture lottery when you play lottery P with probability small p and lottery Q with probability 1 minus p. And the rational agent U will have preferences between gambles. And we write P greater or equal, and this squiggly greater sign, only if you strictly prefer P to Q. So this one stands prefer. So you prefer P to Q. If two lotteries, and you say that you strictly prefer P to Q, if two lotteries are indifferent, then we write P tilde Q. So this is for indifferent. And the expected utility is just a number of plausible axioms like completeness, transitivity, continuity, independence. And then preferences are an expectation of a utility function. That's all it is. And then we just compare the expectations of utility function to identify which gamble is more preferred. The theory is normative rather than descriptive. It suggests how a rational agent should behave, but or should formulate beliefs, but does not tell us how they actually behave. And expected utility U of P of a risky gamble is then P strictly preferred to Q only and only if when utility of P is greater or equal than utility of Q. Okay. Attitudes towards risk. And the solution towards what type of gamble to choose usually controlled by your attitudes towards risks. And risk-neutral agent or risk-neutral decision maker is indifferent about fair bets, meaning that you don't really care about the risk, so you will take always a bet that gives you the higher utility. Risk-averse agent, on the other hand, a person that prefers certainty over fair bets. If you formulate it in the terms of the shape of the utility function, it corresponds to the case when utility function is concave. So utility function has this type of shape. In other words, expectation of the utility is always smaller than utility of the expectation of the gain. So x here is the outcome of the gamble, and for the concave function we have this Jensen's inequality. And risk loving is the opposite to risk averse. It's a person who prefers fair bets over certainty. So always takes the most aggressive bets regardless of the uncertainty associated with those bets. And again, the way that choices are made by you depends on your preferences and your attitudes towards risk. Let's look at Ellsberg Paradox. It's another paradox that shows that probabilities can be counterintuitive. So you have two urns. One urn has 100 balls with 50 red and 50 blue. So you have 50 red and 50 blue in one urn. And then another urn, urn 2, you have a mix of blue and red. And you do not know the proportion of blue and red in the second urn. And then the question is, which urn would you like to bet on? People do not like uncertainty. And when this question is asked, most of the people prefer the first urn for which we know the proportion of red balls and green balls. Although you don't know, maybe in the second urn, all of the balls are blue and you win the game whenever you draw a blue ball. So this is phenomena that shows how people try to avoid uncertainty. Let's look at another paradox called St. Petersburg Paradox. And this is the one that demonstrates that we actually need utility functions to properly resolve the problem of decision making. So let's ask the following question: what are you willing to pay for the following game? I toss a fair coin, and when the first head appears on the t toss, I pay you 2 to the power t dollars. So let's say I toss and you get tails, second toss tails, third toss head. So you get 2 to the power $3. Okay. So first, let's calculate expected return on this game. And expected return is that with probability, so probability of heads appearing on toss t equals to 2 to the negative t, okay? And so the gain from this gamble is 2 to the power t, and the probability that the heads appear on the toss t is 2 to the minus t. And you remember this game can go infinitely long, so the expected gain over the entire gamble is infinite sum, 2 to the power t times 2 to the power negative t, and t goes from 1 to infinity. And this is just sum of ones. This is a divergent series, which means that it doesn't have a finite sum. So essentially the expected gain from this gamble is infinity. And Bernoulli was the first one who constructed this one, and then he asked the question, would you really pay infinite amount of money to play such a game? And I don't think any of you would say, yes, I would pay infinite amount of money. And let's take practicalities out of the question. Let's say you take all your wealth, everything you own, and you put it on the table and say, okay, I'm gonna bet everything I have to play this type of gamble. And of course not. Of course, people don't do that. And that's another demonstration that people do not make a decision just based on the expected return rather than apply some utility function and then they take expectation of the utility function to make the decision. So rather than looking at the expected return from this gamble, we're looking at the expected utility of the return of this gamble. And Bernoulli was the first one to study and was the first one to suggest the use of utility functions. And of course, if you apply utility function, something like risk-averse utility function, then so let's say this is your x and this is your utility of x. So at some point, basically your utility will start growing. So let's say, if you win $1 million, that's enough for a happy life for the next few years, and that's all you really need. And then you say, okay, maybe after $1 million, my utility stop growing, and then based on this utility function, then you can make a more realistic calculations of how much you would be betting on this type of a gamble. Let's consider another paradox called Allais Paradox. And Allais was an economist, and he proposed this paradox in 1952 when he attended a symposium in Paris on risk and economics. And here is two gambles that he presented. Gamble 1, when you win 5 million with certainty, and gamble 2 has three possible outcomes: 25 million with 10% probability, 5 million with 89% probability, and nothing with 1% probability. And then we have another set of two gambles, gamble 2, 3, and 4, where in gamble 3 you win 5 million with 11% probability and you get nothing with 89% chance, and you win 25 million in gamble 4 with 10% probability and you win nothing with 90% chance. And if you do the rational calculations, if you prefer gamble 1 to gamble 2, you always have to prefer gamble 3 to gamble 4. We're going to show it on the next slide, how we make these calculations. However, when actual humans were presented with those gambles, they would always choose gamble 1 when they were presented with choice of gamble 1 and gamble 2, but they were presented with the choice of gamble 3 and gamble 4, they'll choose gamble 4. So when they presented one set of gambles, they showed risk aversion behavior, and then they were presented the second pair of gambles, they were risk seeking. So this is risk aversion, and this is risk seeking behavior. So they were inconsistent in how they make choices. They go from risk aversion to risk seeking. In other words, they switch their attitudes towards risk depending on how the gambles were formulated. So let's do the calculation and show that this relationship will hold. So we're gonna define three things. We're gonna define three probabilities, P1, P2, and P3. So that's the probability of winning $0, $5 million, and 25 for two of the gambles. And then we're gonna define utility function. So again, we're gonna have a utility function for $0, 5 million, and 25 million. And just for the convenience, we're gonna set for 0, utility will be 0. For 25 million, the maximum possible win is gonna be 1. And for the number in between, for 5 million, we're just gonna call this number u. And now let's calculate the difference in expected utilities between two of those gambles. So we're gonna calculate expected utility of the first gamble and expected utility of the first gamble and second gamble. We're gonna call them P and Q. And it's going to be difference between probability of winning 5 million. So remember, that's utility of 5 million. And P2 minus Q2 is the difference in probabilities of winning 5 million between those two gambles. And then P3 minus Q3 is the difference in probabilities of winning 25 million times the utility of 25 million, which equals to 1. Plus, of course, we have probability of difference in probability of winning $0 times 0, so this term just doesn't count. And if we compare gamble 2 and gamble 1 using this formula, then the difference in gamble 1 and gamble 2 is going to be 0.11 times u minus 0.1. And the difference between gamble 3 and gamble 4 is 0.11 minus 0.1. So the difference in expected utilities is exactly the same, which means that if you're consistently making your choices, then if you're a risk-averse person, you always should prefer gamble 1 to gamble 2 and then gamble 3 to gamble 4. And vice versa, if you're a risk-seeking person, you should be taking gamble 2 and when you presented the first choice, and you should be taking gamble 4 when you presented the second choice. And so the order is the same given the value of u. And if your utility satisfies u less than 0.9 divided by 0.11, which is 0.9, you take the riskier gamble. So you decide how risk averse you want to be. You decide for what's the value of your utility for 5 million. And if it's less than 0.9, then you take risky gamble. So gamble 2 or gamble 4. And if it's greater than, then it became less risky gamble. So you take gamble 1 and gamble 3. But again, regardless of whether you're risk averse or you're risk seeker, you always should be taking your choices always have to be consistent. So gamble 1 should be paired with gamble 3 and gamble 2 should be paired with gamble 4. And they should not be mixed as most of the people do. Okay, so let's talk about a set of utility functions called power utility functions. And we're going to talk about the specific utility function called constant relative risk aversion. And this is also quite widely studied by Kahneman and Tversky in their work. And this formula for the utility function has the following form. W is the wealth, so utility of wealth, and the utility is parameterized by this parameter gamma. So W1 minus gamma, power 1 minus gamma minus 1 divided by 1 minus gamma. And then there is a special case, which we'll study more closer, which is a logarithmic utility. So it's a concave function. It corresponds to the risk aversion behavior when gamma equals to 1. And we will see that this utility function, the logarithmic utility function, leads to what is called Cayley criterion, which is quite often used in decision making. Okay, so let's look at this special case when utility is just the log, and we're gonna consider a binary game, and you win this game with probability p, and you lose the game with probability 1 minus p, or we're gonna call it q. And then the question is how much money you should be betting if you present it with such a binary game. And the optimal size of the bet in such a binary game is 2p minus 1. And let's see how we come up with this number. So you play this binary game with probability p, you gain omega if you bet omega. Let's say your wealth is just 1, and the fraction of your wealth, omega, is just omega. So with probability p, you gain this utility 1 plus omega, so you add omega to your wealth. And with probability 1 minus p, you'll lose 1 minus omega. So you take omega away from your wealth. And again, instead of just using 1 plus omega and 1 minus omega, we use the logarithmic function. This is our utility function. And this is a concave function, which you try to maximize with respect to this value of omega. And the optimal value, you just take the derivative and set derivative to 0. There's one critical point in this function, and this critical point is going to be p minus q, or in other words, 2p minus 1. So under risk aversion behavior, if you have this logarithmic utility function means the more wealth you have, the less utility you get from this wealth. Then the bet size in this binary game should be 2p minus 1. Okay, let's talk more about the scaling criterion. Let P denote the probability of a gain, and O be the odds. And odds, you remember, is probability of not winning divided by probability of winning the game. And then we can generalize the Cayley criterion into the asymmetric case when you pay out A when you win the game and pay out B when you lose the game. And then the expected utility with probability P, you add B times omega to your wealth, and with probability 1 minus P, you take away A times omega from your wealth. And then the optimal solution, again, you just take the derivative of this function, you set it to 0, and you find the optimal solution, which is this number, b times p minus aq divided by ab. And usually in the simplified case, the original case we talked about was a equals b equals to 1, and then you get the original Cayley criterion to p minus 1. But a more common case occurs when a equals to 1 and the market odds equal to b equal to O. And then the rule becomes P times O minus Q divided by O. So again, this is a case when you lose 1 unit, and when you win, you win O, which is the just odds of the market. So that's the generalization of this Cayley criterion. So let's look at an example. So you have two possible market opportunities. The one where it offers you 4 to 1 when you have a personal odds of 3 to 1. So what does it mean? It means that if you win, you get $4 on top of your $1, and the chances of this happening is 3 to 1. So if you play this game 4 times, then 1 game you win, 3 times you lose. And another scenario when it offers you 12 to 1, again, if you win, you get $12 on top of your $1 that you put as a bet. And then you think that your odds are 9 to 1, meaning that if you play this game 10 times, then you win 1 time and you lose 9 times. And expected return of this scenario both offering 33% gain. And in terms of maximizing long-run growth, however, they're not identical. So let's do the calculations and see how they differ. So this is a table. We have two scenarios, scenario 1 and scenario 2. Again, market offers you 4 to 1, and the chances are 3 to 1. The probability of winning this game is 1/4, 21%. And then if you calculate optimal allocation, so it's 1/4 times 4 minus 3/4 probability of losing divided by 4. So you remember it's p times O minus Q divided by the odds. So 1/16. So you have to be putting 1/16 of your wealth in this scenario. And under the second scenario, you have 1/10 chance of winning, and 9/10 is the losing. And then if you plug those values into the formula, you get 1/40. So optimal omega star is 1/40 here, and in this case omega star is 1/16. Again, you expect the return is the same in both scenarios, but the bet size should be different because two games have different risk profiles, and you as a risk averting agent should be betting less on the scenario with higher risk. So that's what it ends up doing.